Let's do a few problems. So this problem says, suppose the ski patrol lowers a rescue sled and victim having a mass of 90 kgs. So these two together weigh 90 kg down a 60-degree slope. That's a pretty steep slope at constant speed. So this guy is being lowered at constant speed. What does that mean if you're going at constant speed? Acceleration is 0, so the net force is 0. Okay? And you're moving in this direction, so the net force in this direction is 0. Okay, so so this shows you so there's a normal force acting on the person, okay? And so those are all the forces acting on this object. The tension, the friction force, the weight, okay, and the normal force, okay. Now this component of the weight cancels the normal force, and this component of the weight is what's relevant to us, okay. And this is mg sine theta. Okay. This is mg cosine theta. All right, so since the person is being lowered at constant speed, this must cancel these two forces. Okay, so that's what's going on. Okay, so the coefficient of friction between the sled and the snow is 0.1. How much work is done by friction on the sled as the sled moves 30 meters? Okay, so we're going to calculate the work done by all the forces. Okay. So you can calculate the work done by individual forces. You can calculate the work done by tension, friction, this one, the normal force, and all that. And you just saw the last chapter, the work energy theorem, the net work done by all the forces. If you add up the work done by all the forces, that shows up as change in kinetic energy. Okay, is the kinetic energy of this person changing? No. So the work done by all the forces should add up to 0. Okay. You'll see that this guy does positive work. The force of gravity does positive work. It's this component of gravity does positive work. This component of the gravitational force does 0 work. This guy does 0 work. So this guy does positive work. And these two guys do negative work. So the net work done by these two guys should cancel the work done by these guys. Okay. All right. So how much work is done by friction force as the sled moves down 30 meters? So the friction force is acting in this direction. It's a kinetic friction force. There's the displacement. And the angle between them is 180 degrees. So the work done by any force is Fs cosine theta. You've seen that. So this is the friction force times 30 meters. Okay. And what is the friction force? Okay. So, okay, I'm going to actually write this. So the work done by any force is that. Okay. Friction force is mu k times the normal force, and the normal force is equal to the normal force is equal to that. So work done by friction force is mu k times mg cosine theta okay. Now there's two angles going on. Mg cosine theta, this is theta, and the work done, we'll call this phi. Okay. Distance s times cosine phi. There are two angles going on. Yeah. Theta is the angle of the incline. Phi is the angle between the displacement and the force. Yeah. Phi is 180 degrees, so this is -1. Yeah. So the work done by friction is mu k mg cosine theta times s. 0.190 kgs times 9.8 meters per second, cosine 60 times 30 meters. And this is work, so that's in joules. Okay. Oh, and there was a -1 from cosine phi. -1 from there. So minus 1,323 joules. Okay. Everybody understand that? Yeah. Again, there are two angles going on. Mg cosine theta is this angle theta. The work done by friction force depends on this angle phi, which is 180 degrees. Okay. So this was the friction force, this was the displacement, and this was the angle between the force and the displacement. Okay, so there's the work done by the friction force. How much work is done by the rope on the sled? Okay, so there's the tension which the rope is applying, and again, the tension is they're going this backwards, so we'll have to first calculate the work done by the, we'll calculate the work done by the gravitational force first. Okay. Work done by the gravitational force. Oops. This is mg sine theta and the displacement. Okay, so the work done by gravity is just mg sine theta, and the angle between the two is 0 degrees, so that gives cosine 0 is 1, and s. And so the work done by gravity is 90 kgs times g is 9.8 meters per second square, sine 60 times 30 meters. And all those units work out to joules. All right, now let me show you something else. You could have calculated the work done by gravity by doing this. There's the force of gravity, mg. There's the displacement, and that angle is 90 minus 60. Okay. So I'll write that. So there's the force of gravity, and there's the displacement, and this is 90 minus theta. Okay. So the work done by gravity could also have been calculated mg times s times cosine 90 minus theta, which is sine theta, mgs sine theta. And that would work out exactly the same as this. Okay. All right. Now, part B, you want to calculate the work done by this tension. Okay. There's the friction force. There's mg sine theta. Okay. Now, the net force in this direction is 0. So mg sine theta minus the tension minus the friction force is 0. So the tension in the rope is mg sine theta minus the friction force. And the friction force is mu k times the normal force. And the normal force was mg cosine theta. Okay. I'm going to go back to the diagram. See, the normal force was equal to mg cosine theta, where that's theta. All right, so the work done by tension, now there's the tension, so work done by tension is tension times S times cosine 180 minus, and the tension is mg sine theta minus mu k mg cosine theta times S times minus 1. No, what cosine 180 was minus 1. Okay. So this is equal to, I'll pull out mg sine 60 minus mu k times cosine 60 times S. So there's the work done by tension. Yep.
What is that beside the W?
I'm sorry?
What is that like the W beside the W?
There's no W. This is mu k.
No, the all the way up to the top. Yeah.
Oh, subscript tension. Okay. All right, so let's copy this. So this is the work done by tension. Minus 90 kgs, 9.8 meters per second square, sine 60 minus 0.1 times cosine 60 times 30 meters. the tension, work done by tension is 9,685 joules. All right. The net work done is the net work done by gravity plus work done by tension plus work done by friction plus work done by the normal force. Those are all the forces acting on it. Okay, so there was gravity, there was a normal force, there was tension, and there was friction. What is the work done by this guy? I didn't calculate that.
Just that G cosine theta.
No,
Times 30.
okay, the work done by any force is the magnitude of the force times the displacement times the cosine of the angle between the force and the displacement. Huh?
Zero.
Very good, very good. Force S times phi. This angle was 90 degrees, so that's why it does 0. Okay, normal force always does 0. Mhm. That's right. All right, so now we'll track all of that. There's the work done by gravity, 22,915 joules. Work done by tension is that negative 9685. I don't know, did I do a calculation wrong? Work done by friction is 1,323. And then work done by the normal force is 0. These don't add up to 0, so I don't know where I went. What did I do wrong?
I'm getting a different number for the
Tension?
tension, yeah.
What are you getting?
559.
No, that's an even worse problem. These two should add up to 22,000. Huh?
At 21,500.
Yeah, that's more correct. You got 21,000?
590.
Okay. Yeah. Okay. So that's correct. And these should add up to 0, and they would add up to. So let me see, where did I go wrong? Yep, 21,500. Okay. And so these should add up to, let's see, plus 1,000. And they do add up to 0. Okay. the net work done was 0. Okay. Let's see, is there anything else we need to do? What is the total work done? Yeah, so that's part D. Okay. So we we illustrated the work energy theorem. Any questions on that? Okay. So it takes 500 joules of work to compress a spring 10 centimeters. What is the force constant of the spring? Okay, so they tell you the work done to compress the spring, the work done. Yeah, by the way. So here's a spring. The applied force is in this direction, and the spring force is in the opposite direction. Okay, so when you're compressing your spring, you're applying a force that's equal to the spring force. Okay, so the applied force is equal to the spring force in magnitude, and the magnitude of the spring force is kx. Okay? Okay, so the work done is the applied force dx, and we'll go from 0 to x equal to minus 10 centimeters, okay, or x final. So kx dx, 0 to x final. So work done by the applied force is kx squared by 2, 0 to x final. Okay, so what this means is x final can be negative or positive. You do the same amount of work whether you stretch the spring or compress the spring. Okay, and so the spring constant is twice the work done divided by the compression or stretching you did. And you did 500 joules of work. And how much did you compress the spring? Okay, and what units would you put it in? Meters. So 0.1 meters squared. And so this is 10 to the minus 2. This is 1,000. Okay, so Newton meter equal to 10 to the 5 Newton meter. Okay, so that's the spring constant. Okay, do you guys have any sense for this thing? It's 100,000 Newton meter. Is it a strong spring? So it's a very strong spring. So let's, so most of your weight is about 500 newtons. Okay, so 100,000 newtons divided by 500 newtons, that's 200 people would have to hang out onto the spring to stretch it 1 meter. That's what that number means. Okay, you'd have to apply a force of 100,000 newtons to stretch the spring 1 meter. Okay, so that's a strong spring. All right. So this problem says a bungee cord exerts a nonlinear elastic force. Okay. So the spring force is minus kx. This is called a linear force because it depends linearly on the deformation of the spring. Okay. So if the spring force was like that, that would be a nonlinear force. Any nonlinear term is a nonlinear force, and those problems are hard to solve. Okay. So for instance, again, what I'm saying is this is easy to solve. This would be hard to solve. Okay. Okay, so there you go. So the bungee cord is exerting an elastic force like that. There is the nonlinear term. Okay. For small deformations, this term generally is smaller than this, and it behaves like a spring. Okay. So, and K1, this bungee cord is that, and K2 is that. Okay. So actually these signs are flipped, so this should be negative and that should be positive. Okay, so there's a typo there, it looks like. All right, anyway, this should be negative, okay, so they should both be. Okay. Now the question is, how much work must be done on the cord to stretch it 16.7 meters? Okay. So here's the bungee cord. If you stretch it, the bungee cord will apply a force in this direction, and you have to apply a force in the opposite direction, okay, to stretch it. So the applied force and the bungee force, this should be minus 204x minus 0.233 x cubed. So again, as you stretch it in this direction, the bungee cord is applying a force in that direction. There is the linear term and there is the nonlinear term. Okay, so the applied force is 204x plus 0.233 x cubed. Okay, what are you going to do? You're going to apply this force. How much work must be done on the cord to stretch it 16.7 meters? So you're going to pull on the bungee cord and stretch it 16.7 meters. 16.7 meters is roughly the width of this room. Okay. So essentially you're jumping off a bridge. Yeah. So let's see, what is the work done? The work done is dx x fine. Okay. All right. So the work done is 204 x squared by 2 plus 0.233 x to the power 4 by 4, 0 to x final. Okay. What was x final? How much did you stretch this bungee cord? 16.7. Very good. Okay. Okay. So the reason I wrote them separately is, you see, most of the work is done against the linear component of the force. Okay. The nonlinear term contributes a small portion here. Okay. So that's the work done. And this works out to so that's the work done in stretching the bungee. Okay. So this problem says, how fast must a 3,000 kg elephant move to have the same kinetic energy? So how fast must a 3,000 kg elephant move to have the same kinetic energy as a 65 kg sprinter running at 10 meters per second? By the way, so this is a world-class runner, and 10 meters per second is roughly 25 miles an hour. Discuss how the larger energy is needed for the movement of larger animals could relate to metabolic rates. Okay. So so the kinetic energy of the elephant should equal the kinetic energy of the sprinter. So the speed of the elephant is equal to mass okay. So you bring that there, and then you'd have to take the square root. Square root of that is that. So this is 65 kgs over 3,000 kgs. So the elephant is running at 1.47 meters per second. Okay, that's roughly your walking speed. Okay. Now, the elephant can't run too fast because of its large mass. The energy it would have to produce would be a very large amount. And the problem is, okay, so when you're running and stuff like that, you're about 20% efficient, meaning for an output of 20 joules of running energy, you're producing 80 joules of heat, and getting rid of the heat is a problem. So that would be the problem. All right, this problem says, calculate the force needed to bring a 950 kg car to rest from a speed of 90 kilometers an hour in a distance of 120 meters. So this is a typical stop. Okay. So before we do this, let's convert all these velocities to 90 kilometers per hour. So we want to convert that to meters per second. And 1 hour equal to 3,600 seconds. Okay. Now, here's an equation from one of the previous chapters. Okay. This is the final velocity square is equal to initial velocity square, acceleration times stopping distance. Okay, so we will calculate the acceleration is v square minus v naught square you're stopping and your stopping distance is 120 meters. Okay, so you need a acceleration of negative 2.6 meters per second square. And you can see that g is 10 meters per second square, so this is about 26% of g. Okay, so the braking force applied is a quarter of the weight of the car. Okay. Calculate the force needed. So the force needed is mass of the car times the acceleration. And we're calculating this, the magnitude of the force, mass times acceleration. And again, I'll write the acceleration as 2.6 into g divided by 9.8 meters per second square. So the braking force is, like I said, 26.6% of the weight of the car. All right, now, so suppose instead the car hits a concrete abutment at full speed and is brought to stop in 2 meters. Calculate the force exerted on the car. Okay. Now, you know that if you brake over that distance, you don't get hurt. On the other hand, you run into a concrete wall, you get hurt. What is happening is, if this distance is much smaller, the acceleration is much higher. And large accelerations are what hurt you. Okay, and when you hit a concrete wall, the car might stop in 2 meters. You go and hit the steering wheel and you stop in a much smaller distance. So the accelerations you experience are much larger. Yeah. Why is the car stopping over a distance of 2 meters?
The physical compression of the car.
That's right. And you hit the steering wheel, okay? You don't compress as much. And every time you compress, you're hurting yourself. Okay. All right, so the acceleration is v square minus v naught square over 2x minus x naught. And so 0 minus 25 square over 2 times 2. And this time, so the acceleration is 156.25 meters per second square. 16 Gs. Okay. And that kind of stuff can be fatal. Okay. Okay, this problem says a small block of mass 200 grams starts at rest at point A, slides to B where its speed is that. Okay, so it slides to B and its speed is that. Then slides along the horizontal surface a distance of 10 meters before coming to rest at C. What is the work of friction along the curved surface? What is the coefficient of friction along the horizontal surface? Yeah. Okay, now we sort of have been proved this. We'll actually prove this next chapter. The work done by gravity on an object. You know, so let's say an object falls like this, mg h. The work done by gravity is the force times displacement, and the angle between the two is 0 degrees. Cosine of 0 is 1. So the work done by gravity is mgh. Okay, when an object falls through a distance h. Now, what it turns out that even if you fall along a curved row path, what is relevant is the vertical height you fell. So the work done by gravity when this goes from here to there is mgh, where h is that height. Okay. All right. So this fellow is sliding down. What are the forces acting on him? mg, the friction force, and the normal force. How much work does this guy do?
0.
0, because as the thing is curving, this force is always normal to the displacement. Can we calculate this guy's work? Yes, we can. We know how far he fell down. Okay, and we want to calculate the work done by the friction. Okay, so what is the work of the friction along the curved surface? So the net work done. What is the net work done? Net work done by all the forces. Hmm? I'm sorry? No, it's work energy theorem tells you final kinetic energy minus initial kinetic energy. Okay, initial kinetic energy was 0. They tell you what the speed of the object is at the final point. Okay, so we know this. Okay? So now let's see how that will help us. So what are the three forces acting? The friction force plus the normal force plus gravity. Okay. The initial kinetic energy was 0. The work done by normal force is 0. Okay. And the work done by friction force is what we are interested in. Okay. Work done by gravity was mgh. What kind of work does friction do? Positive, negative, 0? No. Friction forces always do negative work, so this had better come out negative. Okay? So minus 0.2 kgs, 9.8 meters per second square. It fell 4 meters. Final kinetic energy is 1.2 kgs and 8 meters per second. so you see that works out to negative, okay, negative 1.4. So the work done by friction force was, as expected, negative 1.44 joules. Okay. Now they ask you, what is the coefficient of kinetic friction on the horizontal surface? So now you're going at 8 meters per second and you come to rest. Okay? So let's look at part 2 of the problem. What does the coefficient of friction tell you? I'm sorry? Yeah, how sticky the two surfaces are. The stickier the surface, the faster it'll stop. Okay. So if this stopped in 5 meters, that means mu k would be higher. Okay. All right. mg, and there's the normal force. Okay. Let's first calculate the acceleration. V square equal to V naught square plus 2a x minus x naught. Final velocity is 0. Yeah. So 0 minus 10 x minus x naught is 10 meters. So acceleration is negative 5 meters per second squared. The acceleration was pointing in that direction. Yeah. And what is it that's what is the only force acting in the horizontal direction? The friction force. Okay. So the friction force is equal to mass times acceleration. The friction force is mu k times mg. Equal to 0.51. What are the dimensions of mu k? I'm sorry? Yeah, no dimensions. So see, that cancels with that. Yeah, no dimensions. Acceleration divided. Okay, you guys following this? I know some of you guys are getting restless, but I don't want to stop in the middle because I'm recording. So let me do 2 more problems and then we'll stop. And we'll give you a break. So this says a person in good physical condition can put out 100 watts of useful power for several hours at a stretch, perhaps by pedaling a mechanism that drives an electric generator. So you can be on a bicycle and you can do work at 100 joules per second. How many people would it take to run a 4 kilowatt electric clothes dryer? Okay, so number of people times power of a person should equal the power of the dryer. Of a person. Okay. So 4 kilowatt is 4,000 watts. 100 watts. So 40 people would need to pedal to get your clothes dry. Yep. So that's one of the places where you could save money. You should dry your clothes on a clothesline. Yeah. Clothes dryer are energy hogs. How many people would it take to replace a large electric power plant generator, which is 800 megawatts. So 8 million people would need to pedal their bicycles to produce the same power of that of the Hoover Dam. Yeah. Okay, so this problem says the man of the preceding problem consumes approximately 10 million joules of energy per day in maintaining constant weight. What is the average power he produces over a day? Okay, compare this with the power production when he runs up the stairs. Okay, so to run this person, okay, you need, so this, to run this power person, you need 1.05 into 10 to the 7 joules in 1 day. 1 day is that many seconds. Okay. So this is the energy that you have to give the person constantly. Okay. Hundred and 21.5 watts. Okay, and most of that, so that's the energy consumption per second, and most of that gets turned into heat. Some of that energy is being converted to stored chemical energy and all that when you do have digestion and all. But so you're all having to get rid of 100 joules of energy per second as heat. Otherwise, you would warm up. Okay. All right, so we'll stop here.